Welcome back. In this session, we will be discussing about the electron microscope grades and supporting films. So let us look back. When we started our lectures, we started talking about the electron microscope. So there we discussed about the various parts of the electron microscope and also the proper procedure of using it. That includes the alignment and proper usage of the instrument. Then we moved on to the specimen preparation where we discussed about several other things including sectioning, ultramicrotome and so on. Still one thing is pending in the sectioning that is called the staining. That we will discuss once we finish the discussion about the grids and supporting films. The next topic of discussion is the grids that are literally takes our specimen into the microscope. So this is like um, a substrate that can help us to take the grids inside, and then the supporting films are the ones that will be laid on the grids. So together the EM grids and the supporting films will form one unit. So in this lecture we'll discuss about the EM grids, what is it meant for, what are the types of EM grids available, and where do we use each specific grid, and what are the limitations and applications of it. And once we are done with maybe next part, I will talk about the support films. So that will conclude the entire discussion on the EM grids and supporting films. So here is about the EM grids. So EM grids, as we know before, it is of a circular shape, but the word the grid is a little confusing to us why the name grid is given. If you look at this, the picture of the EM grid, you can see that it is composed of one thick rim around it and then supported by a crossbars. These crossbars is what we call as the grid. So together to just represent this arrangement, we call the entire system as the grid. Now, the grid has two components here, the rim part and the grid part. So this rim part is of no use for us in the electron microscope, especially the specimen is concerned. So that means the specimen has to be confined in this area. Then what the question arises, what is the purpose of this rim? This rim is used for handling the grade. So that means if you are just handling the grade, the forceps that you are using or the tweezers that you are using can be used to just hold the grid at this place alone. So that means your specimen which is confined to this area is still safe when you are just taking the grid in and out of the microscope. So this rim is like a very crucial, and whenever you are handling the grid, you have to keep in mind that this is the area where you have to just handle with the tweezer. Then as you can see, there is like a central bar here that divides the entire grid area into four quadrants. This central mark, maybe at the end of the session you can zoom in and see that this is marked distinctly, the center of the grid is marked distinctly, and you can also see a marker here. So the this marker and the center of the grid is present in almost all the commercial grids available, and this is not very important for you for a routine user because this has like a limited applications. This grid bar will be helpful for you to see whether you are at the center of the grid or not. And anyway, the modern microscopes are coming with what is called the grid locator. In that sense, this is having limited applications now. Moving back, as I said, the grid has the uniform diameter 3.05 millimeters diameter, and that we discussed several times in the earlier sessions. Now, the next one is what are the requirements for the grids? One requirement is 3.05 diameter. Second one is it should be made from conductive and magnetic materials. So these two words are very important here. First, let us see why it has to be conductive. So the word conductive includes the conductor that is having good conductivity of both electrical and magnetic nature, thermal nature. So both the conductor, if you just go back and see, all the good electrical conductors are good thermal conductors as well. So this is what you have learned in your high school. So This conductor is representing two arms. One is the electrical conductor, the other one is the thermal conductor. So now let us see what is the role of the each of these, why it has to be electrical conductor, why it has to be a thermal conductor. So as you all know, the electron microscope grid is supposed to be placed in the beam of the electrons that are highly accelerated. So in that process, it could be that some of the electrons get accumulate on this. So these electrons will create a charge on it, and this charge can cause some kind of deviation to the electrical electrons that are coming out, and that has to be prevented. And that means we have to make sure that the electrons will not be accumulated on the grid itself. So this can be done by using a conductor. So that means any electrons accidentally accumulated on this will be flowing back to the ground. So that means taking a conductive material, electrical conductive as the material for the electron microscope grid will prevent the possibility of accumulation of charge on the grid. Then, how come the thermal conductivity of the material helps us? The thermal conductivity, again, the electrons when it bombards the grid bars, it can create some heat. So this heat is most unwanted thing in the electron microscope in several aspects. One, the heat can destroy our sample. Second, the heat can cause some kind of thermal expansion, thereby destabilizing the stability of the conducting film or the support film that we lay on it. So soon we are going to talk about the support films here. So just as I now just take it granted that this grid will have a support film laid on it. So this support film has to be stable on this grade, and that will be done only in the absence of any external movement or that causes the disturbance between the contacts of the support film and the grade. So in order to minimize that contact, any heat that is generated here should not cause any thermal expansion in the electron microscope grade. This thermal expansion may destabilize the support film. So in other words, what happens is this support film starts floating on the surface of the grade. So that means there is a movement of the film, whereas the grade stays stable. So this is looking like a capturing a picture of a moving object. You know the consequence of the capturing the image of a moving object. So in order to minimize that, the entire cause for this is the heat generated. So in order to minimize this kind of drifting, we need to just minimize the heat generated here, and that will be done again by the thermal conductivity of the metal that you are taking. So any heat that's generated because of the bombardment of the electrons on the grid bars will be carried away outside the electron microscope grid. So that means the electrical conductivity and thermal conductivity of the grid are well taken here. That is the reason any grade material should be made from conductive material. Next question is a magnetic material. Why it should be a magnetic material? Actually, it should be a non-magnetic material. There is a misnomer here. So why it should not be a non-magnetic material? A magnetic material, let us say if I take like a iron material grade. So what happens, this iron may influence the magnetic field nearby it. So remember, this grid is placed between the conductor, the condenser lens and the objective lens. Those lenses are typically magnetic fields. So if you keep a magnetic material here, this magnetic material may influence the magnetic field at the conductive lens and the objective lens, and thereby um, it can cause a malfunction of the instrument or slightly misalignment of the instrument. So in order to keep that, it should be a non-magnetic material. This is a misnomer here. Just read this as a non-magnetic material. So this is the whole process. It should be a conductive material and non-magnetic material. And then what are the materials available for it? So it is the most common or popular grades are the copper. Even though we have the gold grades available, the platinum, the nickel, and the rhodium. As you all know, the gold and platinum are the cheapest ones. That's why it is like less expensive. No, not least used. It's not like that. It's the other way. The copper is the one that is mostly available, but then the question arises where the gold, platinum, nickel and rhodium will be available, will be used. So the gold, especially the nickel, will be used especially in specific cases where you will be going for what is called immunolabeling, gold immunolabeling. So it is known that sometimes the gold may interact with the copper, and that's why we don't want to have any specific interaction between the immunogold and the copper. In that case, people prefer to use the nickel grades. So as I said, for most general applications, copper grade is sufficient, but for specific applications, if your sample demands, there are other options available where you can just go for the gold, platinum, nickel and rhodium. So that's having said about this EM grades, one more thing to discuss before moving on to the support films, that is the nature of the grid itself. As you can see here, this grid has a solid rim around it and the grid bars just stretch along the entire space. The grid, apart from this having the grid bars, should have nothing in between. So that means in each of the square that you are seeing should have an empty space. But in order to give a more stability, what people does is they give a quick coating on it. So that means a quick coating will just bifurcate or just distinguish the top side of it and the bottom side of it. So if you don't have anything, just grid bars alone, the top side and the bottom side look alike because there is no extra coating on it. But what happens usually is this copper grid will have a flash coating typically made of rhodium. So that rhodium coating will make a distinction between the top view and the bottom view. Then the question arises, how do you choose which one to choose, the grids facing it or the coating facing the specimen? So typically we choose to prefer the grids facing the surface, the specimen. Then the question arises, being very thin nature, remember it is 3.05 millimeter, and how do you distinguish which one is a top, which one is a bottom? So that will make use of the property what is called the reflection. So if you just look at the top view, what you can see is a film or a coating on the top of which you have the grid bars. On other side, what you can see is only the coating. So now this is the question between a rough surface here and a smooth surface on the other side. So now to go back, any metal that has a good polishing will be very shining, and poor polishing or the rough surface will have less shining. So that means one side of the grid will be shining, the other sides will be less shining. This is what we call as a dull. So given the shining surface and the dull surface, we prefer to take the dull surface on the top, so that the specimen will have good contact with the grid bars. Remember, if you see a shining side, that shining side will not allow the grid bars to come in contact with the supporting film or your specimen. So that will limit the constraints of the usage. Next part is the support films. This support films, the function of the support films is to act as the substrate for the sections that you are using, or the specimen, or let it be protein or the nucleic acid. And what are the properties or the requirements of the support film should be? It should be thin, it should be electron transparent, and should be strong. Let us see one each at a time. Why it has to be thin? The thin is the requirement of getting the high resolution. So that means if the support film itself is thick enough, the electrons may not penetrate through it, so thereby limit the functionality of the electron microscope. Then why it has to be electron transparent? For the obvious reason, if it is electron opaque or electron translucent, the electrons may not pass through it without any difficulty or without any deviation, and again that will pose a constraint on the working of the electron microscope. Then why it has to be strong? If it is not strong, means it should be like it can be either broken or it can be just start sliding. Both of them are most unwanted in the electron microscope. So in order to keep the electron microscope grid firm, like a firm, we need to have the support film to be a thin, electron transparent and strong. So here are we have like several grids here. So we have the hexagonal grid, we have the mesh grid, and the mesh grid has two categories: the 400 mesh and 75 mesh. And we also have a slot grid here, and we have also what is called an index grid or defined grids. So in total, we are going to discuss about all these grids. What are they good for? What are their strengths? What are their weaknesses? Before going further, let us look at the proper grid itself. So as I said before, the grid has a green, the rim bore, rim area, and we have grid bars. So usually it is made of the number of grid bars, and the number of grid bar density is what listed here, a 400 mesh. So if we have a 400 grid bars per inch area length, then we call this as 400 mesh. So naturally, when you come to the 75 mesh, it is going to have only 75 grid bars per inch. So some people also translate this into per area. So they say that this 400 mesh is going to have 400 squares or grid squares per unit inch. Likewise, 75 mesh is going to have 75 grid area squares per unit inch or inch per unit area, that is square inch. So that's about the grid bars. And now usually in principle these grid bars, the grid area that you are seeing should be empty, but in order to give a better support of this grid will be just coated with a very flash coat of either copper or palladium. So then that copper will just act as a cushion for this, or maybe a surface supporting surface for this. Now naturally we prefer to just take this grid area for keeping our specimen. So then it is a task to identify which one has a flash coating and which one has the grid bar. So don't expect this to feel by touch, because given this 400 mesh per inch length, the length of each grid bar is going to be something like 40 microns, and the spacing between each grid bar is going to be 60 microns at 40 mesh. So such a small mesh, and it is not visible for a naked eye. So for a naked eye it looks like a complete continuous surface. So then how to distinguish which one is a grid surface, which one is a coat surface? For that we depend on the reflectivity of the property. So naturally the one that has the grid bars will be rough in surface. The one that is having like a uniform coating will be smooth in surface. Now the question is how to identify a smooth surface versus a rough surface. So we all know that the smooth surface or the polished surface is highly reflective than unpolished surface or a rough surface. So now given that property, the one that has a dull side is what we have to just use for the specimen. The one that is a shining side is the one that has the metallic coating on it. So this difference you have to keep in mind for all the grids. Now come back here and just have a comparison between hexagonal grid and mesh grid. So the name says the hexagonal grid is going to have the mesh of hexagonal shape, whereas the square grid is going to have the mesh of the square shape. Then the question arises which one to choose between hexagonal grid or the square grid, isn't it? Once you have only one choice, you always stick on to that. Whenever there are two, you want to know what are the strengths and weaknesses of it. Let us compare the strengths of the square area. So let's look at the square grid. So if you are recording an electron microscope experiment, usually it happens that you move from left to right, and once you reach the end of the rim bar, you just make a translation here and then reset to the left part and again scan at the surface. So in that experience, if you just start from here and just keep moving, you will be just encountering a grid surface and then a grid bar and a grid surface, a grid bar. But take a note, the grid bar is coming only for a transient time and you are just moving along without much interruption. Let us see how this experience goes when you go to the hexagonal grid. Let us choose this area. So you have like a wonderful area here. You start here, and then for a considerable time what you encounter is the grid bar. And again when you come here, you will see the mesh area, and again you will encounter a mesh bar. the grid, the mesh viewing area, the mesh bar, the viewing area, the mesh bar. So that means your view will be interrupted several times by the presence of the mesh bar here. The same thing happens even if you start here, somewhere here. So again, you will be encountering a least area. So this is considered as one limitation of the hexagonal grid. So does that mean that hexagonal grids has to be discarded at all? No, not at all. So when you just consider the support film, just to recollect, every grid has to have a support film on the top of this grid bar. So when there is going to be a support film on it, remember the support film will have only 4 anchoring points of this square mesh, whereas when it comes to the hexagonal grid, it is going to have like a 6 anchoring points. So each of this intersection will just act as anchoring point, or maybe here it is supported by 4 sides, whereas it is supported by 6 sides. Now, the question rises, which one can give us a better stability to the supporting film? The one that has 4 anchoring points, the one that has 6 anchoring points. Definitely we say the one that is going to have 6 anchoring points can give us a better stability to the film. So in that sense, the hexagonal grid is preferred over the square grid. So now we have seen the square grid and the hexagonal grid. Now let us look at between the density of the meshes. So here I have chosen the square grid for the demonstrating the density of the meshes. So here it is 400 versus 75 mesh. The same thing can also be obtained for the hexagonal grid as well. So that means it doesn't mean that only square grids can be available only in the 400 to 75 mesh. Even the hexagonal grid is available from 400 to 75. So what I have shown here is 400 to 75 is only two of the possibilities. You can have the mesh from 75, 100, 150, 200, 400, and maybe 600 as well. So beyond which I have not seen any grids that has beyond 600 mesh. So these are the limitations in the options available for you. Now let us compare between 400 mesh versus 75 mesh. You can see the 400 mesh are dense in nature, and naturally this can give us a better stability to the film as compared to the 75 mesh. So 75 mesh are going to have like a fewer square grids here, and this is going to give us a lesser anchoring points, thereby giving a less support for the support film. So that means the 400 mesh can give us better stability than the 75 grid. Does that mean that this is the universal choice? No. Just look at the viewing area. This is the viewing area and the viewing area here. So naturally you can see a bigger viewing area in the case of the 75 mesh than the 400 mesh. So this limits the use of the 400 mesh for a smaller particles, whereas when your particle size or the molecular dimension goes bigger, the 75 mesh will be the right choice. So that's about the 3 types of grids that you have seen here. Next comes the slot grid. So this slot grid doesn't have any grid bars, and this will be mostly used for the sections. So if you have a section here, this grid bars will come on the way, and that will be just acting as an obstacle for you, and this can give you an uninterrupted surface area of a maximum viewing area. So if you recollect the ultramicrotome presentation, the sections that are coming from the ultramicrotome are of the ribbon size, and that will fit very well in the slot grid. So mostly this will be used for the sectioning part. So having said that, let's move on to the index grid. The index grids are different, less like your square grids. Only difference is every mesh area, the square mesh that you are seeing is properly or uniquely identified by a combination of an alphabet and the number. So this will help us to relocate a particular slab and mesh area for future reference. So that means if you are just seeing an interesting feature in one particular area, you have to just note down the coordinates of that particular mesh, and later on if you want to show that to your boss, you can bring your boss and just go back to the same section and you can be able to see it. Is that possible to do the same task in this mesh? mesh. That is not possible because this area which is on the top, when you just reload the grid, don't have to be here at the top. It can be any of the positions that you see around the peripheral of the grid. So in that case, what you are thinking about the interesting area may not be here. It can be in any place around this circle. So that will be avoided by just with the help of the index grid, where you are depending on the coordinates of the mesh area rather than the position of it. So having said that, we also have what is called a calibration grid. The calibration grid is usually used for two purposes. One, to calibrate the magnification of the microscope. The second, it is used for correcting the astigmatism. So I have not brought the pictures of the calibration grid here, but you can just Google it and can find out more details about the calibration grid. So let's go back and talk about the grids. One type of grid that I have not discussed so far is a calibration grid. So maybe I didn't bring the picture here. You can Google the calibration grid. The calibration grid will have like a predetermined spacing between the rods and the bars, and those spacings it's typically made of the carbon, and the spacing is like a fixed one that can be used for calibrating the grid. So let me see if I can bring some images in the next presentation, and then we will start the discussion about the calibration grid in the next section. So what we discuss in this present lecture is we discussed about the importance of the electron microscope grid, and we just put some rules on the materials that to be used for making the electron microscope grid. And once we identify what are the films in the material that will be used for the electron microscope grids, we talked about the classification of them. The grids can be of the square shape, the mesh shape, or the slot shape, or the index grids. And we have seen the applications of each of these. Apart from this, we also discussed about what is called a calibration grid. So next session we will discuss about the support films, various types of support films available, and the applications in each of them. Thank you.